Okay, hello. So we're doing chapter 7 of CCNA 1 today, and so it's all about IP addressing. So we're going to look at the use of IPv6 addresses to provide connectivity in small and medium-sized businesses. And so, of course, to look at IPv4 addresses properly, you need to look at binary numbers as well as converting between binary and decimal. You need to describe the structure of IPv4 address, including network portion, host portion, and subnet mask. We're also going to look at comparing the characteristics of the types of transmission for IPv4, so unicast, broadcast, and multicast. And we're going to look at public, private, and reserved IPv4 addresses. Now, we're also going to look at IPv6 addresses, and so and how they provide connectivity. And we're going to explain the need for IPv6 addressing, describe the representation of those addresses, compare the types of v6 addresses, and configure global unicast addresses, and describe multicast addresses. And so then from there, once we've got the addressing sorted, of course, normally you need to test that it's all working well, and so connectivity verification we'll be using some ICMP tools to do that, which are mostly ping and tracer out. So IPv4 addresses. And so, of course, because it's on these numbers are stored and used by computers, it's binary numbering. So, of course, binary numbering is just bits which have two possible values, 0 and 1. And so an IPv4 address is 32 binary bits, but of course when it's displayed to us, it's displayed with 4 8-bit octets, and translated into dotted decimal notation, as it's called. And so, as I said, as you can see on the screen there, all the IP addresses have a number, a dot, another number, and so on. So that's each octet is separated by the dots. So of course with 8 bits the maximum value you can have in any octet is 255. So basically a bit of revision, I'm assuming you know this, but anyway, can't hurt. So we're talking about positional notation here, and so basically we're talking about how we're just sort of explaining in detail how numbers work. Of course, the reason we're doing this in decimal is so we can then sort of relate it to binary in the next few slides. And so basically, as you can see from here, that we're talking about the base number or radix, and so of course we're talking about decimal, so of course it's 10. And then the second row is basically the exponent, or it's also their position in the number, and so you always count from the right, from 0, 1, 2, 3, 4, etc. And so basically from there, then we do 10 to the power of 0 for this column, and of course it's always going to have a value of 1. 10 to the power of 1, of course, is always itself. 10 to the power of 2 was 10 squared, so 100. 10 to the power of 3, of course, is 10 cubed, so it's 1,000. So they're the values of all of your columns in a number. And so basically here they've applied it, and so we've got 1 1,000, 2 100s, 3 10s, and 4 1s. And so, of course, we end up with 1,234. So it's all I know, fairly trivial. So, of course, with binary, we have, of course, the base number is now 2 because there's 2 possible values as opposed to decimal where there were 10. And so, again, the position number is the same. We start at 0, it's just that we're showing you more columns this time. And so then, of course, we calculate the positional value by doing 2 to the power of this position number. So 2 to the power of 0, anything to the power of 0 is 1. 2 to the power of 1, of course, is itself, so it's 2, 2 squared, 2 cubed, and so on and so forth, 2 to the power of 4, 5, 6, 7. And so these are how you get your column values for a binary number. And so again, if we actually use these positional values as the top of this next table, we can then convert a binary number into decimal. And so we've got the column with a value of 128 with one entry, 64 with one, and then the rest are all zeros. So basically, to get the value of that binary number, all we need to do is add together 128, sorry, and 64, and of course that adds up to being 192, because they're the two columns that have a 1 in them. The zeros, of course, are always 0, and that's trivial addition. So to convert a binary number into decimal, it's basically that process we were looking at. And so again, 1, 1, 1, and then 6 zeros. Of course, that's how you end up with 192. Then you do it next for the next octet and figure out what that number is, and so on and so forth. And so that's how you would do it. Now, to convert a decimal dotted decimal notation number into binary, of course, the process is sort of reversed. And so basically you need to look at the value of the number, and then is that number that we've got larger than this column here? If it is, you add a 1 to it. So that's what this is here. You got n is greater than or equal to 128. You put a 1 in if it is. If it's not, you put a 0. Then you go to the next column. Now, of course, if you've got a 128, you actually need to subtract 128 from the number that we've been supplied, and then you just go to the next column and repeat, but with 64, then 32, then 16, and so on and so on. And so that's how you do your translation. And so some examples. And so again, we've got the number we saw before, 192. So you would go through. 192 is greater than 128, so you put a 1 in the column. You then subtract 128 from 192, and then you will be left over with 64. And so 64 is greater than and equal to 64, so you put a 1 in the column there, and the remainder was 0, so that's why all the rest are zeros. So here we've got 168, and so basically what's happened is, of course, 168 is greater than 128, so you do that, and you have number left over. 168, 128 from 168 is pretty easy actually. So you've got 40 left over, and so 40 is smaller than 64, so you put a 0. It's greater than 32, so you put a 1, then you subtract 32 from that 40, and so that would be 8. And so 0 there, 8 is exactly equal to that, and so then the rest are zeros, and so on and so forth. And so that's how you do your conversion. Now, that's enough for binary and number conversion. Now we're going to talk about the actual addressing itself and how it's organized. And so an IPv4 address is hierarchical. I think I have mentioned this before. And so there is a network portion, one network portion, followed by one host portion. Now, where the boundary exists between that network and host portion is variable, and so that is actually the coming topic in Chapter 8. We'll be talking about subnetting. But here we've basically got a network number of 192.168.10, and then the host portion is host 10 on that network. Now, all devices on the same network must have an identical network number, and the subnet mask helps devices identify what the network number is of their number. And so we will come into that shortly. So the subnet masks. 3 IPv4 addresses must be configured on a host, and so the first one is their actual IP address. Then there is the subnet mask, and then there is the gateway. That's what's required for a host to be able to talk to other hosts on the same network as well as other hosts on remote networks. Now, of course, this needs to be a unique number. Now, this subnet mask is basically tells us where the boundary between the network number is and the host number. Now, from the previous slide, as it said, the first 3 octets are network number and the last octet is host number. And so that's exactly what this subnet mask here is telling us, is wherever there's a 1 in the subnet mask, in binary of course, that is part of the network number. Where there's a 0 in the subnet mask, that is part of the host number. And so as you can see, 255 is actually the highest value you can have in an octet. And so that's all all 8 are ones, and so all of the first octet is network number. Same with the second, same with the third. 0 there means that none of the fourth octet is part of the network number. So that the only other option is that it's part of the host number. So a subnet mask will always have the same pattern. It will have a string of ones followed by a string of zeros. That's the only pattern it have. One string of ones followed by one string of zeros. That's the only pattern it ever has. And so this tells us the network number is 192.168.10 and the host number is 10. The gateway, of course, is the IP address of the router on the local network. And so if this host wants to talk to a host on a different network, so on a different network other than 192.168.10, it will need to talk to the router, and the router will forward it to that other host, that remote host. Okay. Now, basically, of course, computers do everything in binary. And so, as I said, the pattern for a subnet mask is a string of ones followed by a string of zeros. And so this is how a computer will line them up, and it will actually do, I think it's probably the next slide, a logical AND. Yes. And so basically this is how a computer calculates its network number, is by doing a logical AND. And so if you've ever done truth tables, basically for an AND to be true, you need both inputs to be true for the result to be true. Any other, as you can see down the bottom here, a 1 and a 1, you get a 1 result. Any other bit combination, there's only 4 possible bit combinations with 2 bits, you'll always get a 0. So what basically happens here is the first bit in there's both ones there, and so that will carry down. Second bit, again, both ones there, that will carry down. Now, of course, the last 6 bits, there's a 0 in the top, so that will always end up being a 0. So what's actually happened is, of course, 192, all of this octet is network number, so it's translated straight down. And it's the same with the second octet, because this is all ones. The only time you're going to get something other than the 1 is when there's a 0 there, and so it will end up being the same number. Third octet, again true, we're looking at number 10, and so only 1010 on the end are different to the zeros, and so that's what's carried down there. Now, this part of the subnet mask, you can't get a 1 because every column has a 0 in it. And so that's basically the network number is 192.168.10.0. And so that's how a host figures out what network it belongs to. And of course, when it's got a destination IP address, it will run that destination IP address with the subnet mask. And if it ends up with the same network number, I'll talk directly to it. If it ends up with a different network number, I will use the gateway to talk to it. Now, there is another way of specifying the network portion of an address, and that's called prefix length, or it's sometimes called CIDR notation. Prefix length is actually a IPv6 term, and so it's sort of copied back to this. And so, as you can see here, this subnet mask is 255.0.0.0, which of course means the first 8 bits here are ones, and the last 24 bits are zeros. And so 8 ones / 8. And so basically here, that's a typical A-class mask. This is a B-class mask where you've got 8 bits and 8 bits, zeros and zeros, and so 16, and so on and so forth. Pardon? And so when we work through subnetting a C-class address, this is how our masks can go. Now, the longest mask you can have is a 30-bit mask, or 255.255.255.252, and that's the longest mask you can have, because that's the smallest network you can have, because they're 2 usable addresses. So basically, if you look at this row on the third octet here, when it comes to a subnet mask, basically, there's 255, of course, is possible, but 0, 128, 192, 224, 240, 248, and 252 are the only possible numbers in a subnet mask. That's the only possible numbers. Now, in IP addressing, there are 3 major types of addresses, at least as related to a network. And so the network address, which of course what we calculated 2 slides ago, and you can tell the network address because it's got all zeros in the host section. And so that is the network number. So 192.168.10.0 is the network number. Come on. And there is also, if you have all ones in the host section, that will make it the directed broadcast address for that subnet. So as you can see down the bottom here, for the same subnet as we were looking at before, 192.168.10.255, that's what's called a directed broadcast, and so that's a message that could be sent to every host on that subnet. And so those addresses cannot be used. And so the network number is, of course, used by the router as a destination in a routing table, and so you can't actually apply that to a host. Broadcast, of course, is used as a destination for all hosts on a subnet, so you can't apply that to a host. And so the host addresses are actually where you've got any other bit combination other than all zeros or all ones. And so in this case, because there's 256 possible addresses from 0 through to 255, basically every number from 1 through to 254 is a usable host number on that subnet, and so you've got 254 possible hosts. Now, how do we assign addresses to hosts? Now, there's 2 major ways. There's either manually or automatically, and so manually is where someone types it in, 192.168.10.10 with its mask and its gateway, and away you roll. That's great, it does work. But it's also done by humans. We all make mistakes, typos, etc. You've seen me do typos. And so we try to keep those hosts with static IP addresses to a minimum, but there are some that do need it. And so you certainly do need to do these things, but you try to minimize it as much as possible. The other side, of course, is automatic, or which most people actually call DHCP, or Dynamic Host Configuration Protocol. And so what happens there is when the host is powered on and once the networking is up, it will actually send out a DHCP discover message saying, hey, is there a DHCP server out there? And then a DHCP server will reply with an offer saying, hey, I'm here and this is an address you can use. And then the host will then send out a DHCP request, and then the server will send an acknowledgement saying, yeah, done deal. And so the DHCP server provides an IPv4 address, subnet mask, and default gateway, and typically other information as well, at the very least a DNS server. And so the server leases that address to the host, and so, you know, it could be a day, it could be an hour, it could be 20 days. If the host is powered down or taken off the network, the address is then available to be used in the pool again. And so basically you've got these addresses that can be used, or they may not be. Now, there's 3 ways that hosts can communicate using IPv4. So there's a unicast, which is basically a single source sending that packet to a single destination. In this case, we're sending data to a printer. So there's a broadcast where a single host sends it to every other host on the subnet. So as you can see, that packet's actually gone to everyone else. And then a multicast is sort of a cross between the two, where one host will transmit to a group of interested hosts in so as a multicast, basically. So unicast packet, of course, will have the source IP address of the host that sent it and the destination of that particular host that wants to talk to. And so it's all very simple, easy to get along with. With a broadcast, most of the time, it will be source address, again, will be whichever host sent it, so it's this one. And then the destination is typically all ones in the IP address. So as you can see, 255.255.255.255. And so that would actually go to every host on the network. Now, routers don't forward broadcasts, by default at least. And so that's as far as it will go. It will stay on that subnet. And so that's what's called a broadcast domain. Wherever that broadcast goes, that is the domain of where a broadcast may go. So broadcast domain. And then there's a multicast, and so there's a special group of addresses set aside. So 224.0.0.0 through 239.255.255.255, and so they're reserved especially for multicasting. And so basically, in this case, the source is this host here, and these hosts are interested in seeing that message, and so they've joined a group. As I said, it's and so the host will send it, and only these hosts will take notice of it. Now, there are actually specialized routing protocols, especially for multicast routing propagation, and so typically the multicast won't go very far, but you know, it is possible to route them over a WAN if you need to. Now, there are different ways that the addresses are organized, and so back in the early 90s, they actually discovered that they were running out of IP addresses for the world. I'm going to say there's 4,000 total IPv4 addresses, and you know, well, these days there's over 7 billion people. Did I say 4 billion? And so straight away there's a shortage. And so basically since the early 90s, they've been creating plans to sort of mitigate the problems. And so one of the solutions they used was they actually created a special kind of addresses called private address blocks. And so these are set aside that anyone can use at any time as they like, as long as they don't connect to the internet. So they're not routable, so no ISP will route packets to or from those network numbers. Introduced in the 90s due to depletion of IPv4 addresses, used only in internal networks, must be translated to a public IPv4 address, which is of course the opposite of a private one, to be routable. And so that's what your router at home does. It does what's called network address translation. And so the request for comments for that standard is actually 1918. And so there's one A-class address that's been set aside for private address blocks, so the 10 network. So that's 16 million addresses. There's 16 B-class networks that each with 65,000 hosts that are there as well. And there is 256 C-class networks that are available for this private addressing. And so, of course, if you've looked at your address at home, it's probably 192.168.1. something. And so that is what's commonly on home routers, because they're pre-configured when you plug it in, typically. Okay, now there are other specialized IPv4 addresses, and so there is the 127 network, which is used so you can ping yourself, basically. So there's the loopback address, as it says, and so if you ping 127.0.0.1, as long as all the software in your computer is right, it will just test that your software is working. There is a range set aside for linked local addresses. Now, if anyone's ever seen a 169.254 IP address on your computer, something's probably gone wrong. And so basically what happens is, or what the situation normally is your host is booted up, it's sent out a DHCP discover message and gotten no reply. So there's no DHCP server available. And so then it will actually grab 169.254 and it will then do some mathematics, I think, with the MAC address of itself, and then it will actually grab an IP address. And so if you've got a whole pile of hosts on that network that the DHCP server has obviously failed or turned off or whatever, the hosts should be able to talk to one another, but of course they won't be able to talk to the rest of the world. But at least talking to one another at least makes it somewhat possibly useful. And there's also a test network address set aside, so it's 192.0.2.0/24, and so that's used for teaching and learning, a bit like example.com is. Okay, now, back in 1981 when the IPv4 first came out, in RFC 790, the addressing space was divided into 3 classes of addresses that were usable as host numbers. And so there was A, B, and C class. I think I might have mentioned it earlier. Now, basically, an A class address has the first octet is network number, and then the 3 last octets are host number. And so that means there's 128 A class networks, each with 16 million hosts per network. Network 0 and network 127 are actually unusable. We've already spoken about 127 because I look back. Network 0 was unusable because we actually deem all zeros to be the entire internet. Now, so there's actually only 126 usable Class A networks, and of course one of them is private. So that's A class. With B class, basically, so A class actually takes up half the addressing space of the IPv4 addressing range, and so yeah, there's actually roughly 2 billion addresses in the A class range. Now, Class B is a quarter of the addressing range, and so that's there's 65,000 hosts per Class B, because basically the first 2 octets are network number, the last 2 octets are host number, and so 2 to the power of 16 gives you 65,000 hosts per, and so yeah, there's quite a number of B class addresses. And then C class, which is an eighth of the total addressing space, is where you have the first 3 octets are network number and the last octet is host number, and so that gives you 256 address space, but minus the network number and the broadcast that we spoke about earlier, there's 254 usable hosts per C class address. And that's, as I said, that's probably what you've got at home. And so the way that they've chopped this range up is actually, if you look at the first octet, an A class always has a 0 on the first bit. A B class always has a 1 0, and a C class has a 1 1 0. And so that's actually how those addressing ranges were devised. And so back in the dark ages, you know, early 80s, that was actually how hosts figured out what their network number was. They'd look at the first 3 or 4 bits in the first octet, and if it started with a 0, hey, I've got an A class, and so on and so forth. Now, so as I said, A class is half of the addressing range, B class is a quarter, C class is an eighth, and then there's also D and E class. Now, D class is that range that we spoke about earlier for multicasting, and so that's that 224 to 240, and so that's fine. And E class, they call that experimental, which basically means they didn't know what to do with it. Now, classful addressing, as you can see, was, I'm going to say, the people who designed it didn't have the foggiest clue what was going to happen to the internet in the 90s and beyond. And so basically they redesigned how the addressing worked, and so they introduced classless addressing, and it's called CIDR, which is classless interdomain routing. And it allowed service providers to allocate IPv4 addresses on any address bit boundary prefix instead of only class A, B, and C. And so basically it allowed us to decide what we needed. And so it's a lot more flexible. Now, how do we get an IP address? So basically there are registries around the world that look after the addressing for their areas. And so as you can see, there's the American Registry for Internet Numbers, ARIN, that's North America, and there's a whole pile of others. In our area, we belong to APNIC, which is Asia Pacific Network Information Center, and so there's of course ones for Africa, South America, basically, as well as Europe, and so on. So and so that's where you can get your addresses from. But sadly, with AppNic, they ran out of addresses years ago, IPv4 addresses. Now, IPv6. So IPv6 was designed because we were running out of IPv4 addresses. And so instead of a 32-bit number, so 2 to the power of 32, as I said, 4 billion addresses, they've quadrupled the size of the address. Now, there's 4 times as many bits. Of course, that doesn't mean we've got 4 times as many addresses available. Of course, it's exponential. And so 340 undecillion addresses, which is a horrendously huge number. And so basically, there's apparently several thousand addresses per square meter of the Earth's surface, or 1 per grain of sand on the planet. All kinds of wonderful things like that. You'll get quoted. But yeah, it's going to last us a while. And so basically, because we've been running IPv4 for 40 years now, they've figured out what didn't work very well. And so with IPv6, clean sheet, they've actually changed the way it's used to optimize it, and it's actually a much smarter system. And so it solves many of the limitations of IPv4, adds enhancements like auto address configuration and things like that. So why did they do it? As we said, the use of the internet is growing and growing all the time. You know, there's the Internet of Things. So all of those things need to have an IP address. And of course, IPv4 was running out of addresses. One of the solutions to that, of course, was NAT, Network Address Translation. NAT was a very good solution, but it wasn't perfect. It actually used to breaks quite a few things. And so it's not fantastic. And so, as I said, the Internet of Things is going to be using lots of addresses. Okay, so how do we migrate from IPv4 to IPv6? Now, the most common method is called dual stack. And so basically what that means is on every device, you configure both an IPv4 and an IPv6 address. And so they've got both stacks running at the same time. And so they'll use whatever they can. I think if you've got both running, it will normally prefer IPv6. Now, if you need to get IPv6 packets across an area that is IPv4 only, you can actually tunnel it through. And so basically what happens is you've got the IPv6 packet, and it will actually have an IPv4 header put in front of it, so it can get through the IPv4 section. Then when it gets back to the dual stack area or IPv6 area, it can take that header off and then continue on its journey. There is also NAT64, but that's less and less common these days, the use of that. And so that's how you can get an IPv4 only area to talk to an IPv6 only area. Okay, so as we said, IPv6 addresses are 128 bits in length. Dotted decimal notation would be pretty ugly, because you've noticed that, you know, with dotted decimal notation, you know, some numbers can be 1 number and others can be 2 and others can be 3. And so with 128 bits, your addresses would accordion strangely. So they display them in hexadecimal, which of course is a base 16 number. So with that, each character in a hexadecimal number represents 4 bits, from 4 zeros through to 4 ones. So that's 0 to 15 basically. And so when an IPv6 address is displayed, it's basically 4 characters a colon, so that means 16 bits, or they call it a hextet. And so basically they have a string of those. And so from there, that's the way it's displayed. Now, they can actually be abbreviated, which we will talk about a bit later. Now, so these are the way that addresses would often be displayed. So 4 numbers, colon, 4 numbers, colon, 4 numbers, etc., etc., etc. But you can see there's a lot of zeros there. So there is actually ways that we can shorten those. Of course, that's a way that a computer would deal with it, the entire 128 bits. Of course, in binary, really. Now, the first thing you can do is you can actually lose the leading zeros. And so you keep all your colons in there, and so it will just, if it only sees 3 characters, it will assume that it needs to fill in, 4 ones in front of that, or 1, 2, 3, 12, sorry, ones, 4 zeros in front of that. And this one, because there's 3, that would be 12 more zeros, binary ones in front of that, and so on. And so that will actually shorten that number a fair bit. And that's one way to do it. And there is another way we can shorten it as well. For a long string of zeros, we can actually just put in 2 colons. And so here they've chosen this bit here. So after the DB8 and before the ABCD, they've just put the 2 colons in. So basically they've saved 8 hexadecimal characters. They could have done it there as well, but anyway. But you can only do it once, because basically when you use this notation, the computer will fill it from the front, and then it will fill it from the rear, and then the gap it will fill with zeros. If you have 2 of them, well, how many zeros are going to put there, and how many if it did it for both that one and that one, the computer's never going to know how many zeros to put in each. So you can only do this double colon compression once. And so basically, if you see here, this compression has taken this address down to that. So that's certainly very useful. And now all zeros in IPv4, that meant the entire internet. Well, guess what? That means exactly the same thing in IPv6. And so if you put 2 colons, that means 128 zeros. Okay, so basically there's 3 types of addresses again: a unicast, a multicast, and an anycast. Now, unicast is exactly the same as what we were talking about in IPv4, one source, one destination. A multicast is one source to a group of destinations who are interested. Now, of course, with IPv4, there was broadcast. That does not exist in IPv6. Now, they do actually waste quite a few resources, broadcasts, and so they've basically gotten rid of them. Now, an anycast is basically a unicast address that's been assigned to multiple addresses. This is pretty much the only mention we're going to make of anycast in the entire CCNA curriculum. So, yeah, we don't really talk about it in any great depth. Okay. Now, with IP prefix length, IPv6 prefix length, it's used to indicate the network portion of an IPv6 address. Of course, you've got a range of 0 through to 128, but rarely will you see anything other than /64. So the first half is network number, the second half is host number. And so basically that's how it runs. Rarely will you need to make something shorter than /64. Now, when it comes to unicast addresses, there are actually several ways you can go with that. And so a global unicast is actually the same as a public IP address in the old days. It's a unique internet routable address. So that's basically, what you got in IPv4 if you exclude NAT. Now, there is also a linked local address, and so a linked local address will always start with FE80, and that is equivalent to that APIPA address that we were talking about earlier. And so basically the host will actually figure that out for itself. A global unicast address, you'll either have to get that from a router or from a DHCP server, typically. You can type it in manually, of course, but that, of course, most hosts will actually use one of the other methods. Now, link local basically means you can talk within a subnet to other devices quite happily. Now, unique local is sort of a bit like the private addressing ranges in IPv4, and so you can actually have all three of these addresses at the same time on the same host. You can do that. Now, linked local addresses enable a device to communicate with other IPv6 enabled devices on the same link only, are created even if the device has not been assigned a global unicast address. And so, as I said, they will start with FE80. Now, note, typically it is a linked local address of the router that is used as a default gateway for other devices on the link. Now, basically, what happens is, with most hosts, is they'll grab the FE80, and that's all they use in the first 64 bits. And then the last 64 bits, they will actually uniquely create their own host address. And so there are several ways that they can do it, but EUI 64, I think, is what's mentioned in the curriculum here. And so that is where they grab the 64 host bits, and then they actually put the MAC address into it. So the first 24 bits of the MAC address in the front bit, the last 24 in the last bit, and then actually sticks a whole string, or basically the number 1 in between. And that's how they get a unique number, because theoretically MAC addresses are unique, and so it should all work nicely. And so that's basically the process for giving them an address. Now, so that's a link local we were talking about. Now, with a global unicast address, basically, there's only a small range of those addresses have been used at the moment. Of course, there's under killions of them, and so basically the addressing is handed out in such a way is that, as I said, normally you've got a /64, so the first half is host network number, the last half is host number. But if you go to one of the network information centers and get addresses from them, they will actually give you a /64, sorry, a /48. And so what you can do there is that will be the global routing prefix. And so that will be a unique number that is on your network. And then from there, it will actually, from there, you actually have 16 bits that you can actually subnet with. And so as you can see here in purple, yeah, we've used subnet 1. And so that will be part of that, again, will be your network section, and of course your host section. Again, most hosts decide for themselves what they get, but they just need to learn their network number. Okay, so how do we statically assign global unicast addresses? So on a router, we actually do interface gigabit 0/0, do IPv6 address, and type it in. Now, as you can see here, we've done the abbreviations 2001:DB8:ACAD, a CAD, isn't that cute? :1, and then we've got 2 colons and the number 1. And so this is host number of 1, and this is the network number basically. And so as you can see, we've done a CAD2 and a CAD3 on the other interfaces, and away we've rolled. So you can of course do this statically, and of course this is a much nicer number to type in than any other options, and it's a router, why not? Now you also need to give the prefix length, and so rarely will you do anything other than /64. On a host, you can do manually as well, and so again, same network, different host number of course, prefix length is 64, and of course the gateway address of that, and that will work nicely. Now, you can also do it dynamically as well. Now, when we spoke about IPv6, one of the advantages was auto configuration, and so there's 2 methods you can do that. And so there is the option of stateless, which is called SLAAC, which is stateless address auto configuration, or there's also basically DHCP. Are we going to talk about it next slide? Yes, we are. So stateless or SLAAC is basically when the host boots up, it does not actually send out a DHCP discover broadcast, because we don't do broadcasts anymore. What it does is it sends out a multicast to all routers, and so it's called a router solicitation message saying, hey, is there a router out there? And so if there is a router, which there normally should be, the router will actually then reply saying, here I am, and here's your network number. And so, of course, the host will get that, and then it will create its own host address using its MAC address, and then all is good. It knows who its router is because it's got no packet from the router, and it knows who itself is, and it knows its prefix, all that kind of information, and it works nicely. The problem with it is that, the reply from the router is called a router advertisement. The problem with it is it doesn't learn DNS server. That's about the only problem with it. The other option is basically when you send out a router solicitation message, the router will say, yes, here I am, but send out a DHCP request and get your information from a DHCP server. And so that is another option. So if you want to set up a DHCP server, you actually have to set up the router to reply in the correct fashion to get a host to talk to a DHCP server. Again, when it's talking to a DHCP server, it doesn't broadcast because that doesn't happen in IPv6. It will send out a multicast that a DHCP server will be listening for. Okay, now basically there's three options when it comes to that dynamic configuration. Which is the default mode, is it'll get its prefix number, it will get its network number, and that's all, and no DNS. A second option is basically the host will get its information from the router, but it'll also be said there's more information to get from a DHCP server as well. And so the host will then send out a DHCP request, and that's normally how it would learn the DNS server. Or the router can say, you won't get your information from me, you'll just get it from a DHCP server, so send out one of those requests. And that will basically request the DHCP info. So, the EUI 64 process, this is how we pick a host number. And so basically, as I said, you already know your network ID, but you need to decide your own host ID. And so basically, as I said, it will normally pick the MAC address. You use the first 24 bits and the last 24 bits like that, and it'll actually fill the gap. Sorry, I said 1, but it's FFE. So it's basically 15, 15, 15, 14. And so basically from there, that's how it will pick it out. And then it will actually do a message to say, is there anyone else there using this address? And so when you do that, you'll actually have the network portion that you've gotten from the router, and then you'll have the random number that's been plucked from the MAC address and had extra info put in. Now, Windows doesn't use EUI 64 process. It does its own random number generation, and so it's perfectly all right. But yeah, it's just a little different. Back in the Windows XP days, I think they did EUI 64, but they don't anymore. Now, link local addresses, hosts will have them. Now, again, what will happen is it'll have FE80, and then at least the Cisco device will use EUI 64 for the host section. Now, that's great, but it's also, do you really want to type that number in? And so it's a long number. And so you can actually statically assign the link local address. And so there's actually a command for that. And so you can do IPv6 address FE80::1. That's a lot easier to type in than that other one on the previous slide. And then you just put link local afterwards, and that will actually reassign the link local to be something different. And so yeah, that does make things a lot easier. So as you can see on this router, they've actually used FE81 on all three interfaces. That's fine. But if you had a second router, you'd probably have to use FE82, because those two routers might need to communicate with one another, and they won't be happy if they have the same link local address. So different routers will need to have a different address. So how do we verify address configuration? They're pretty much the same on V4 and V6, except V6 you put V6 in the command. And so show IPv6 interface brief gives you this information. So it tells you each of your interfaces, and it tells you the addressing information. As you can see, this doesn't have manually assigned link local addresses. It's just got the automatically generated ones, but it does have network numbers that we'll put in. Show IPv6 route, of course, is this is the routing table, and so we've got directly connected networks here, and away you roll. And we've done a ping to test connectivity, and so that was successful, so it's all good. Now, multicast addresses. So basically there's two major types. There are basically assigned ones. They're reserved. There's probably a better one, better name for it. And so therefore predefined tasks. So when you send out that router solicitation message, that is actually one that is sent to that FF02::2, because that's what routers will listen for. If you wish to find out who your neighboring hosts are, you actually send out a neighbor solicitation message to this address. So that's where all IPv6 nodes actually listen. Only routers listen on this, and so there'd be one set aside for DHCP, and certain routing protocols have them as well. And so they're all those, they're all the reserved addresses that are used for specific purposes. And then solicited node multicast is where you have, some kind of broadcast or something, well, a video stream or something like that you might route. Now, basically, as with all multicast addresses, you need to map an Ethernet MAC address to the IPv6 or IPv4 address, and so that's actually how a host knows that it's interested in a particular multicast stream. And so as you can see here, the NICs will look at it and say this multicast is not for me, and so the NIC will look at it and just discard it. This one will do the same. This one is interested in it, and so we'll actually then pass it up through the protocol stack to layer 3 and beyond. So connectivity verification. ICMP is Internet Control Message Protocol, sorry. And so there's version 4 and version 6. And so basically they're very similar, but of course rewritten for the different versions. And so messages common to both: host confirmation, destination or service unreachable, time exceeded, or route redirection messages are the most common ones we'll see there. So ICMP is actually where those router solicitation messages and advertisements come from. That's actually, they're part of ICMP for IPv6. And so that router solicitation, router advertisement, same with neighbor solicitation and neighbor advertisement. That of course replaces ARP. ARP doesn't exist in IPv6, and so it's actually the neighbor solicitation messages. And then there's also another one called a DAD, or duplicate address detection. So remember, when the hosts pick their own host section, what they do is, as soon as they've done that, they'll actually send out a DAD message, and they'll say, all right, I've picked this address. Is anyone else using it? And so if no one replies, it's all good. But if someone does reply, they'll just play around. Well, if it's EUI 64, they'll just play around with that number in the middle, the 16 bits in the middle, and change it and say, okay, is anyone using this now? And so that's basically what they do. So you don't get duplicate addresses. Okay, so you can ping the loopback interface. And so, of course, that's 127.0.0.1 for IPv4, or it's colon 1 in IPv6. And so it just checks that your software is all working properly. Of course, you can also ping other hosts, both on your local network and your remote network. The first place I normally ping is, as this suggests, the router. So if I can ping the router, I can ping on the local network, and of course, if the routing work, I can probably ping remotely. So pinging the router is always a pretty decent plan. And so ping basically works. If you type in ping, your machine will send an echo request saying, hey, please, can you send me this information back to make sure, so I know we've got connectivity, and the host will normally reply with an echo reply. Some hosts have actually had that turned off because it can be a bit of a security issue, but yeah, on your internal interfaces is normally all right. So of course, with a remote host, you can ping from this host to that host, and again, as long as it goes through the router, you're sort of making sure it works on a different network. Now, traceroute. Traceroute is very good. So ping is sort of binary. It either works or it doesn't. With traceroute, it basically tells you how you would get from this host to that host. And so basically, it gives you the list of hops that were successfully reached during along the path, and it gives you a round trip time. So basically, how long did the packet take to get to that host and then back again? Now, the asterisk means that they didn't get a reply for that host. Now, that can mean one of two things. Basically, as I said, some routers actually don't reply to ICMP packets because it can be a bit of a security issue. And so you might, if you do a trace route and there's 10 hops in between, you might get some that have stars, and you'll get others following it that don't have stars. And so that just says to you that that particular router doesn't reply to ICMP messages. But if you get asterisks and only asterisks from a point, that says that you can't get any closer to that other host. And so traceroute is actually a very good fault finding tool, because it sort of tells you where you can get and where you can't get, and so it helps you sort of localize where your routing problems might be. So it's a very handy tool. Okay, that's the end of the chapter. And so basically we looked at IPv4 addresses and how they provide connectivity, and we've also done the same for IPv6, and we've looked at some testing utilities so we can verify connectivity. Okay, so there's the logo. So we're done for this chapter. So there will be a chapter 8 video as well, and so that actually goes into subnetting. So yeah, good luck with that. Until next time, see you later.